research paper. And
Yeah.
wow.
Yeah.
It's a big one.
It's ambitious.
It really is.
Yeah.
It's talking about how to build a quantum computer with 1,000,000 qubits.
Mm-hmm.
1,000,000.
That's right.
It sounds like science fiction.
It does sound like science fiction, but
Yeah.
this paper, it really lays out
Yeah.
this plan and this architecture.
Yeah.
They call it the trilinear array.
And what's really cool is that it's building on something we already know how to do
Exactly.
really well.
Like really well.
Like making these teeny tiny transistors.
Yeah, these are the,
Everywhere.
workhorses of
Our phones, literally every electronic device.
pretty much, yeah, all modern electronics.
So, I mean, instead of starting from scratch, they're kind of taking inspiration from technology that's already revolutionized the world.
Exactly. Why reinvent the wheel?
I like that. But before we get into the specifics,
Sure.
why is 1,000,000 qubits such a big deal?
Okay, so it all comes down to building what are called fault-tolerant quantum computers.
Okay.
So imagine you have a regular computer, and every time it encounters just a tiny error,
Yeah.
it just crashes.
Right.
That's essentially what we're dealing with right now in
Yeah.
the quantum world. Qubits, they're so sensitive
Mm-hmm.
that any little disturbance can completely throw off the calculations.
Wow.
So to get to a place where we have useful quantum computers,
Mm-hmm.
we need to be able to correct these errors like on the fly.
Got it.
And that requires a lot of extra qubits,
Okay.
potentially millions.
Okay, so it's all about redundancy,
Well,
like having backup systems in case something goes wrong.
That's a good way to think about it.
Got it. But even if we can build 1,000,000 qubits,
Yeah.
how do we even connect them?
Oh, yeah. That is the huge hurdle.
Yeah.
So each qubit needs its own individual control and readout wiring.
Okay.
And this is completely unlike transistors, which you can easily connect in
Yeah.
series. So this is what people are calling the interconnect bottleneck.
Okay.
And this is where the tiny size of spin qubits,
Yeah.
which is great for packing them in densely,
Okay.
actually becomes a problem. Because now you have 1,000,000 microscopic components,
Yeah.
each one smaller than a virus.
Oh, wow.
You have to try and wire up on a single chip.
It's like trying to stitch together a tapestry with threads thinner than a human hair.
Yeah.
It just seems impossible.
It's a massive engineering challenge.
Yeah.
But this is where the trilinear array comes in,
Okay.
because it's actually kind of an elegant solution.
Okay.
So instead of trying to cram all those qubits onto a flat two-dimensional grid,
Yeah.
which would make wiring a complete nightmare,
Right.
they're saying, what if we line them up
Okay.
in 3 parallel lines?
So instead of a flat grid, it's more like a 3-lane highway
That's a great way to think about it.
for qubits.
Yeah.
Gotcha.
And this simple change in geometry, it has some really profound implications for wiring and for control.
Okay.
So each qubit, which is represented by what's called a quantum dot,
Mm-hmm.
it gets its own dedicated wiring in this setup.
Oh, wow.
So that means that we can optimize the performance of each qubit individually.
Okay.
And we can even control and read out many of them simultaneously,
Okay.
which is really important for speed and efficiency.
Gotcha.
So it's a huge win.
Okay. I'm following you so far. But if everything's in a line, how did the qubits on opposite ends of the highway interact?
Yeah.
Did they have to shout across 3 lanes of traffic?
Well, that's where the concept of what we call shuttling comes in.
The shuttling.
Yeah. So imagine you're physically moving the qubits between these lines
Okay.
to allow them to interact.
Wow.
It's kind of like a really tiny, highly choreographed dance
Oh.
where these qubits are shuffled around to pair up and do calculations.
So it's not just about positioning them strategically, it's about moving them
That's right.
around in a really precise way.
It's-
This is a lot. This is complex.
It is definitely complex.
So how do they keep track of 1,000,000 tiny dancers all moving at once?
Well, that's where the real ingenuity of this architecture comes in.
Okay.
And that's what we're going to talk about next.
All right. I am ready.
Let's get into
So
it.
part 2. Let's go. Okay, so we've got our 1,000,000 qubit highway.
Right.
And we've got our tiny quantum dancers shuttling between lanes.
Mm.
I'm all for a good dance party.
Yeah.
But how does this translate
Yeah, how does this actually...
into an actual working quantum computer?
Well, remember that challenge of wiring up 1,000,000 qubits?
Oh, yeah.
So the trilinear array,
Yeah.
it tackles this head-on
Yeah.
by borrowing a strategy from advanced chip making
Okay.
called 3D integration.
3D integration.
Yeah.
Is this where it starts to sound like a sci-fi movie again?
It might, but it's a real thing.
Okay.
So instead of just having one layer of qubits,
Mm-hmm.
Imagine stacking multiple chips on top of each other, like a high-rise building.
Whoa.
And each layer can then be dedicated to a specific function.
Oh, wow.
So you could have qubit control,
Okay.
readout, even memory storage.
So instead of like a sprawling single-story factory,
Yeah.
we're going vertical.
Exactly.
I like it. And I guess that makes the wiring a lot easier.
Oh, yeah, you dramatically reduce the distance
Okay.
that signals have to travel,
Gotcha.
and you can pack in way more complexity.
Okay, so to control 1,000,000 qubits, even with efficient wiring, you can't have 1,000,000 separate wires coming out.
Right.
That's just not practical.
That would be a nightmare.
Yeah. So what do they do?
So they use another trick called cryo-CMOS circuits.
Cryo-CMOS.
Yeah.
Break that down for me.
So think of them as like super-powered electronics
Okay.
that are designed to work at extremely low temperatures,
Oh, okay.
the kind of temperatures you need for these qubits to function.
Gotcha.
And these circuits are key to something called multiplexing, which is essentially a way to control many qubits with far fewer wires.
So it's like having one conductor directing an entire section of an orchestra
That's a great analogy.
instead of needing a conductor for every single instrument.
Exactly.
Got it. Okay, so we've got the trilinear layout for efficient placement. We've got shuttling for the qubit interaction, 3D integration for streamlined connections,
Yes.
and cryo-CMOS for precise control.
That's right.
It's like all the pieces of this giant puzzle
Right.
are starting to fit together.
Yeah.
I have to ask,
What's that?
what happens if one of those 1,000,000 qubits decides to take a break
Yeah, what if one of them
and stop dancing?
fails?
Yeah.
Does the whole system just stop working?
Yeah.
Well, this is where that dedicated wiring we talked about
Okay.
becomes really important. Because the trilinear array allows for something called on-the-fly reconfiguration.
On-the-fly reconfiguration.
Yeah.
Okay.
So if a qubit goes faulty, you can essentially reroute the shuttling paths around it.
So it's like setting up a detour or a quantum highway.
Exactly.
Wait.
You might lose a few qubits in the process,
Okay.
but the system as a whole keeps running.
And I guess in a system of 1,000,000,
Right.
losing a few here and there
Yeah, it's
isn't really a big deal.
It's not a huge deal.
But wouldn't that require some serious monitoring?
Yes.
To find those faulty qubits in real time?
It would require some very advanced monitoring systems.
Oh, yeah. Okay.
And this kind of brings up a point that sometimes gets overlooked
Okay.
when people get excited about quantum hardware.
Yeah.
Because it's not just about building these amazing qubits and arranging them cleverly.
Right.
We also have to develop equally sophisticated control systems
Okay.
and error correction codes
Gotcha.
to make sure that these qubits are actually doing what they're supposed to be doing.
So it's like we're not just building a quantum computer. We're building the quantum equivalent of a traffic management system.
Yeah, like
Our tech crew.
yeah, almost like a whole quantum city
Yeah.
to house it all.
I like that, a quantum city.
Right.
That's a great analogy.
It really underscores how much work still needs to be done.
Yeah.
But the fact that we're even conceiving of solutions to these problems
Right.
shows how far we've come.
It's pretty inspiring.
It is.
But let's not get too carried away with the engineering marvels just yet.
Sure.
I'm still curious about how this trilinear architecture actually impacts the connections
Yeah.
between the qubits.
Yep.
Is everything limited to just nearest neighbor interactions? Or are there more interesting possibilities?
This is actually one of the most exciting aspects of the trilinear approach
Okay.
because it allows for a much richer set of connections
Right.
than a simple 2D grid.
Gotcha.
So instead of just talking to their immediate neighbors,
Mm-hmm.
the qubits in this system can potentially interact with others
Okay.
that are further down the line.
Oh, wow.
So remember that shuttling system we talked about?
Yeah.
It's not just for moving qubits between lanes.
Okay.
It can be used to create a much more complex web of interactions.
So our quantum dancers aren't just waltzing with their partners.
Right.
They're doing the electric slide across the entire dance floor.
That's a great way to put it.
That's got to have some interesting implications
Oh, yeah, definitely.
for the kinds of algorithms you can run
Absolutely
in a
right.
system like this.
Yeah, and that's what we'll explore next. Because this flexible connectivity,
Yeah.
this is key to unlocking the true power of the trilinear array.
Okay.
And it might just revolutionize how we think about quantum algorithms.
All right. I'm ready for part 3. All right, so I'm hooked on this idea of our quantum dance party.
Yeah,
But let's talk about the music,
sure, the algorithm.
the algorithms. You mentioned this trilinear setup.
Right.
It opens up all these possibilities.
Yeah, it does.
Yeah, so let's talk about that.
So this is where things get really fascinating. not just from an engineering perspective, but like from a theoretical standpoint.
Okay.
The way that we actually design quantum algorithms, it's deeply connected to the architecture of the quantum computer.
Okay.
So if you have a simple 2D grid, you're basically limited to just nearest neighbor interactions between the qubits.
Yeah.
And that really limits what kind of algorithms you can implement.
So it's like trying to choreograph this really complex ballet.
Yeah.
But your dancers can only interact with the people standing right next to them.
Exactly. But with the trilinear array and that shuttling system, you can create much more intricate patterns of interaction.
Gotcha.
So we can have these qubits from different lanes, like meet up, perform some calculation, and then move on and interact with other qubits.
So it's a whole new level of choreography.
A whole new level of choreography.
And that means that we can design much more powerful and efficient algorithms, right?
Absolutely.
Algorithms that can take advantage of this complex dance floor to solve problems in new ways.
Exactly. And not only can we explore new algorithms, but we can also improve existing ones. Like take, for example, quantum error correction.
Right.
This is like super crucial for building fault-tolerant quantum computers.
Absolutely. We need a way to keep our dancers all in sync, even if a few of them trip up or lose their rhythm.
Exactly.
But how does the trilinear array help with that?
So traditional error correction codes, they're usually designed with a 2D grid layout in mind.
Right.
But with the trilinear array, we can actually emulate the connectivity of a 2D grid.
Okay.
By just strategically shuttling the qubits between the lines.
Oh, so we're creating like a virtual grid.
Yeah, basically like a virtual grid.
On top of our physical structure.
Exactly.
Yeah, that's pretty neat.
Yeah, so that gives us access to all of these existing error correction techniques.
So we get the best of both worlds.
Yeah, you can think about it that way.
We get the flexibility of the trilinear architecture, but we also get the robustness of those established methods.
Exactly, and it gets even better.
Okay, how?
Because this unique connectivity of the trilinear array, it might allow us to develop entirely new error correction codes. Codes that are even more efficient and more robust.
That's true, because they're taking advantage of these longer range interactions.
Exactly.
So we're not just copying the old playbook. We're writing a whole new chapter in the story of quantum error correction.
Yeah, I like that.
That's amazing.
And this is just one example of how this architecture could like really push the boundaries of what's possible.
Right. It's not just about the number of qubits.
It's not just about the number.
About how they're connected.
It's about the connections.
And how we can leverage that.
Exactly.
This is so cool. We've covered so much today, from like the really intricate details of the trilinear architecture to like how it could potentially revolutionize quantum computing.
It really is amazing to see how these researchers are pushing the boundaries. They're combining this ingenuity with existing technologies to create something totally groundbreaking.
It makes you wonder what other seemingly impossible challenges
what's next?
Are we going to overcome in the next few decades? What discoveries are just waiting for the right tools to be built?
That's the beauty of science.
It is.
There's always something new to explore.
Yeah.
It's always a deeper question to ask.
Absolutely. And with all this progress happening in quantum computing, it feels like we're just at the beginning.
I think so, too.
Of this incredible journey.
Yeah.
Well, I think that is the end.
I think that's it.
Of our deep dive into the fascinating world of trilinear quantum dot architecture.
It's a mouthful.
It is.
But it's an exciting one.
It is. Thanks for joining us, everybody, and we'll see you next time for another adventure into the cutting edge.
See you next time.
Of science and technology.